This lecture is dedicated to eco-friendly natural rubber latex-based pressure-sensitive adhesives and coatings. Natural rubber solvent dissolved pressure-sensitive adhesive versus natural rubber latex-based pressure-sensitive adhesive. Do they differ? The purpose of publishing this article is to study the behavior and also to compare the performance of natural rubber based pressure sensitive adhesive versus natural rubber latex based pressure sensitive adhesive. Do they differ in performance? Let me address to a general question in anybody's mind. Waterborne adhesives and coatings. Natural rubber latex based adhesive, can they offer the same amount of adhesion, water resistance, heat resistance, holding power, and service life? Can they overcome the mechanical stability problems? Can they replace natural rubber solvent dissolved pressure sensitive adhesives? The answer is yes. Now let us see how the natural rubber based pressure sensitive adhesives are manufactured. The chemical formula of natural rubber is CH3. It is a multiple of a formulation which is shown on the screen. It is available in two forms, emulsion or liquid, which is called as latex, a dry rubber which is available in sheet form. The difference between rubber and latex. Rubber and latex are both elastomers in which dimensions can be changed largely when stressed and which can be returned to their original dimensions after the stress is removed. They fall into the category of polymeric materials. Latex items and rubber items can be distinguished by the method of production. In addition, latex and rubber can be differentiated from each other because latex is the raw material for rubber, so latex should be identified first. Latex. Latex is defined as a stable colloidal dispersion of a polymeric substance in an aqueous medium. The most common latex is the sap obtained from Hevea brasiliensis tree. In latex, there are two systems, namely a dispersion medium and a dispersed phase. In latex, rubber particles are suspended in the aqueous medium. Rubber molecules are present as chains in the structure and, they are free space in between the chains. Latex is mixed with compounding agents like additives added to improve the property of latex. Generally, latex is used to make thin films. Rubber. Rubber is obtained from latex, which is tapped from trees. The most common tree that is used to produce rubber is Hevea brasiliensis. The molecular structure of natural rubber is cis 1:4 polyisoprene. Tapped latex is first diluted and then it is coagulated using an acid. After that, this coagulated latex is compressed in rolls to remove water. The products are raw rubber sheets. These sheets are then taken to process rubber items. Rubber sheets are mixed with compounding agents to impart the desired properties of the final product. Both latex and rubber are waterproof. Have a look at the chemical structure of dry rubber. We see that this is a very long chain molecule with a lot of unsaturation or double bonds in it. Hence, it needs to be processed to break the long chain molecule. Dry rubber adhesive manufacturing process flow chart. Natural rubber latex is filtered, purified, and coagulated. Water and rubber are separated. Rubber sheets are then dried. This is dry natural rubber. The same is masticated on two-roll mill for about 30 to 40 minutes. At this stage, resin plus antioxidant plus plasticizer is added to rubber for about 40 minutes. The mixture is charged to a sigma mixer and a solvent toluene or petrol is added and gradually with continuous mixing for about 3 to 4 hours. After 4 hours, the adhesive is ready. It is stored in barrels, tested and used. Rubber mastication. Mastication, the process by which the viscosity of natural rubber is reduced to a suitable level, is an important step in the mixing procedure. Rubber polymer such as natural rubber requires mastication to reduce their viscoelasticity and to even out variations between different polymer lots. This process can be simulated by a torque rheometer. Compounds with curing agents are tested for minimum viscosity, the onset of scorching, and for the rate of cure. These tests allow the assessment of the initial flow properties of the sample. The torque peak caused by the high resistance of polymer being sheared while still coiled. Then one can evaluate the process of mastication. The figure below combines the two mastication test runs for an easy comparison. Mastication of a natural rubber just under the influence of shear and temperature. Mastication as above but with a additional influence of chemical additive called rancid 7 added to the polymer at a level of 0.5%. This accelerates the breakdown of molecular structure and greatly reduces the mixing energy. Mastication and softening are usually carried out in batches. The operation is done either in a large enclosed mixing machine or on rubber mills. The premier example of an enclosed machine is the Banbury, a registered trademark of a mixer. Consists of heavy steel counter-rotating pedals in an hourglass-shaped chamber, holding up to 1/2 ton of rubber. Rubber mill have two large horizontal opposed closely spaced steel cylinders up to 3 meter or 10 feet long that are rotated slowly in opposite directions and at somewhat different speed. Rubber is sheared and softened in the gap between the pedals and the wall of the Banbury mixer or in the gap between the two cylinders in the rubber. Mastication is an important step in the manufacture of rubber compound. It decreases the viscosity of rubber, promotes good dispersion of fillers and chemicals, and increases the compound plasticity. In this paper, the author summarizes the present knowledge about mastication of rubber and peptizing agents and present the recent work carried out in their laboratories on the topics. It is demonstrated that peptizing agents act in the mechanochemical and thermo-oxidative breakdown of elastomers as radical acceptors at low temperature and as oxidation catalysts at high temperature. You can see the photographs of internal mixer and a two-roll open mixing. Rubber mixing mill. The basic design and construction of the mill has been subjected to continuous improvements which have permitted them to keep pace with the day-to-day needs of the industry. Rubber mill is available in sizes varying from 6-inch into 16-inch to 26 into 84-inch for compounding, warming, sheeting of various grades and types of rubber and other material. In the category of mill, also available in different sizes are refiners, crackers, grinders, rubber breaker mills, and asbestos shettlers. Silent features include chilled cast and rolls, frame, caps, journal boxes in high-grade casting, gear of cast iron or casting, and MS sheet fabricated as per duly requirements, specifically alloy leaded bronze bushing suitable to make heavy separating forces and to go gravity force or flood lubricating systems, rolls suitable for steam heating or cold water cooling, positive pullback fail-safe system for emergency stop, special accessories, strip cutters, stock dividing guides, stock blades, etc. These are the various sizes of rubber mills which are available. They are available from 6-inch by 13-inch, where 6-inch represents the diameter of the roll and 13-inch represents the length of the roll. You get rubber mills up to 26-inch by 84-inch. As per the capacity of the mill, the mixing capacity varies, the RPM of the motor varies, and also the electric connected power. It varies from 7.5 HP to 225 HP per machine. Rubber dispersion needs. Understanding the needs of plastics and rubber processing industry and developing fully indigenous solutions to cater to these needs has always been the prime target. When the need was felt for a mixer capable of hard mixing from process compounding view, now dispersion needles have been developed. Dispersion mixing can be employed in a wide range of material mixing, ranging from low viscosity adhesive to high viscosity rubber. Internal mixer series to a highly developed range of dispersion needles for rubber and other polymer with high productivity and consistently good mixing and minimum electricity. Sigma mixer are needed to produce uniform mixing and needing heavier viscosity material. The Sigma mixer is suitable for many applications like mixing, etc. The Sigma mixer have applications to produce highly viscous materials like different kinds of adhesives. Here are some photographs of Sigma mixer. The essential load required for solvent dissolved natural rubber adhesive. You need a mixing mill, you need a sigma. Mastication on rubber mill connected load is 15 HP for a 12 by 13 size 12 by 30 size of rubber mill, which is equal to 11.25 units. Mastication time is nearly 30 minutes. Quantity of rubber is 12 kg. It is mixed with resin, antioxidant, other raw materials on rubber mill. The connected load of the mill is 15 HP. The total time required is 90 minutes. Total quantity that can be produced is 24 kg. Mixing of dry rubber compound with solvent, toluene or petrol or hexane. The connected load is 35 HP, that is equal to 26.25 kW or units. Mixing time is 240 minutes. Total solution capability of sigma is 48 kgs. This means the electrical energy consumption of rubber mill at 11.25 units into 120 minutes, which is equal to 22.5 units. Sigma mixer, the consumption will be 26.25 into 240 minutes, which is equal to 105 units. Total electrical units consumed 127.5 for 20 kg of dry rubber, that is 5.31 units per kg, which will be roughly around 37.18 rupees per. The manpower cost on rubber mill will be around 4 rupees per kg. The manpower cost on Sigma mixer per hour per person will be around 12.5 rupees per. At this moment, let us study how latex rubber-based pressure-sensitive adhesives are manufactured. Let us have a look at rubber molecule yet again. You see the picture. We see that this is a very long chain molecule with a lot of unsaturation or double bonds in it, but it is available in emulsion form, like the photo shown on your right hand side. Latex rubber adhesive manufacturing process flow chart. Natural rubber latex. It is purified and processed by centrifugal method. At this stage, resin emulsions plus other raw materials in emulsion form are mixed, and the mixing is done a simple agitator for about 30 minutes. Then the adhesive is ready for storing in barrels before coating. The structure of natural rubber particle. Introduction. Based on the reaction of natural rubber towards various chemical treatments and physical techniques, the following structure has been proposed for the structure of natural rubber particle. You can see in the photograph, in the center is the rubber particle. It is surrounded by phospholipid layer. It is followed by protein layer. This is the outline structure of natural rubber. The principle of phospholipids of natural rubber latex are of the hesitant type, and they are strongly absorbed on the surface of the rubber particle. They are thought to be intermediaries by which the proteins are anchored onto the rubber particle. The addition between the proteins and the absorbed lecithin has been accounted for the fact that at the pH of fresh latex, the lipid layers carries a slight overall positive charge, whereas the proteins being on the alkaline side of their isoelectric point are negatively charged, so that the ionic interaction between the two layers is possible. The chemical composition of fresh natural rubber latex. Being a natural rubber product, the composition of natural rubber latex would vary depending on various factors such as clone season, soil conditions, fertilizer application, techniques, tapping frequencies, etc. As such, it is not possible to give an exact composition for the natural rubber latex. However, a typical composition can always be suggested as given below. It is given in terms of by percentage by weight of liquid of latex. Dry rubber content generally 30 to 35%, proteins substance 1 to 1.5, lipids 1 to 2.5, sugar 1%, organic ions 1%, water around 60 to 65%. All these non-rubber substances are distributed between three principal phases. The average percentage of each of these three phases is given below. Rubber phase 35%, aqueous phase 55%, lutoid phase 10%. Lutoid phase can only be seen in fresh natural rubber latex since the lutoid particles which constitute the lutoid phase are very sensitive to various factors such as dilution, ammonization, and heat. Lutoid particles are slightly larger than the rubber particles and are irregular in shape. Chemically, they appear to be chemically they appear to be mainly water. In addition to that, they contain various other substances such as carotenoids, acids, mineral salts, proteins, and even rubber particles. The boundary of a lutoid particle is semi-permeable membrane and hence they are osmotically sensitive. Preservation of natural rubber latex. Preservation of natural rubber latex is normally achieved by adding up to 1% by weight of ammonia. Ammonia is being good biocide has several advantages. It controls the proliferation of bacteria, neutralizes the free acids formed in the latex, helps the precipitation of heavy materials such as magnesium, hydrolysis the interfacial proteins and and phospholipids nearby, making the latex more stable. The hydrolysis of phospholipids has been found to occur more rapidly than that of the proteins, and as a consequence, by the time the latex reaches the latex reception point of the industrial user, the phospholipids of ammoniated and concentrated latex have been converted to fatty acids or soaps. Among the other products, such as amongst the other products, much of the proteins remain. If you like it, you can contact us on our cell phone. You can drop us a mail. You can visit our website. You can reach us on our. You can get in touch on our WhatsApp. You can get in touch on LinkedIn. You can join us on Facebook. You can join us on LinkedIn also. You can talk to us on Skype. You can Visit us and subscribe us on YouTube.